Now that we have a little bit of an understanding of what the derivative is, we can start talking about some slightly more involved derivative rules. So just as a reminder, the derivative is the rate of change of a function. If you give me a function, its derivative function tells you the rate of change at a given input. So we'll talk about derivatives a lot more later, but let's talk about some rules. Let's say we have a function, what we already know. Let's talk about what we already know. If f of x is some linear function like 3x minus 7, then the derivative is just the slope of the line. In this case, it would be 3. That is actually going to be a little bit more relevant to the left-hand side, or to the right-hand side here, but it's good to start off with that knowledge. Okay, so we're going to start talking about some slightly more complicated questions. What if we had something like f of x equals 3x squared minus 7? If we put a squared there. That's not too much different, but it's still something we can work with. But to begin, let's just talk about the rule that we're going to use. If f of x equals x to the n, where n is any number, doesn't have to be a whole number, although we certainly like it when it's a whole number, then the derivative, what we're going to do is we're going to take the power down up front, and then our new power is just going to be 1 less than the original power. And that's the rule. So let's go ahead and use this rule on a couple examples. So let's start with the easiest example we can come up with. How about f of x equals x squared? Well, what do we do to find the derivative? We're going to take the exponent out front, and then our new power is going to be 1 less than the original power, which will be 2x. Okay, so that seems easy enough. Let's do one more kind of big example. Let's name our function something else, maybe g. Let's look at g of x equals something like x to the 100. Then g prime of x is going to equal 100 x to the power of 99. We take the power up front, and then our new power is 1 less. So this rule seems like it's pretty easy to use, but the thing is sometimes, I guess I should say n is any number except 0. It can't be 0. That's good to note. If n equals 0, then x to the 0 just equals 1, which is a constant. So the derivative is just 0. Okay, so there you go. Which actually fits our rule. Sort of. So let's go ahead and look at a slightly more complicated example, because not all functions look this nice. What about if we had something like h of x equals, if we had something, let's say, 1 over x. You might look at that and say, that's not x to a power. Well, the thing is, it kind of is. 1 over x is just the same as x to the power of -1. So once we rewrite it that way, it's really clear to see that h prime of x equals -x to the -2, which is the same as writing -1 over x squared. And just, again, a reminder, taking a negative exponent just means moving it from the numerator to the denominator or vice versa. So there we go. What if we had, we'll say m of x. What if this equaled like the square root of x? Well, how can I write that as a power? Well, the square root is just x to the power of 1/2. Then the derivative is going to be, well, we'll have 1/2 out front, And then what's 1/2 minus 1? That's going to be negative 1/2. When then we can rewrite that if we want to as 1 over 2 x to the 1/2. That's 1/2, which equals 1 over 2 square root of x. And just as one last final example here before we move on to something else, we can also have something like, let's say, m of x. We'll do that again. What if it equals like the cube root of x to the 7? Well, that is just the same as x to the power. Ooh, let's make it even more fun. We'll make it 1 over cube root of x to the 7. Well, that's just 1 over x to the power of 7 over 3, which is the same as, we can move it from the denominator to the numerator by making the exponent negative. That's going to be x to the negative 7/3, which means that the derivative, and now this is where subtracting by 1 becomes a lot harder than you thought it would be. The derivative is going to be negative 7/3 times x to the power of negative 7/3 minus 1. That is the same as negative 7/3 minus 3/3, which is going to end up being negative 7/3 x to the negative 10/3, which if you really wanted to, you could write as negative 7 over 3 times the cube root of x to the 10, if you were really feeling it. I'm not necessarily going to need you to do that. But as we can see, this power rule, even though it seems pretty simple, actually allows us to deal with all sorts of different types of functions. Okay, but I wrote this here, and this here is not it's not just x to the power, it has some other stuff going on. Well, there's kind of two nice rules that we have that will help us take care of functions like this. And I'm going to use some different notation here just so you can see it, because it will show up on the worksheet. So if I write this, something like this, x squared plus 4, this is just telling me to take the derivative of whatever's on the inside. And one of the nice rules we have is that if we have things being added together, that's just the same as taking the derivative of each term separately. So that's really nice. So in order to evaluate this derivative, which isn't just x to some power, all we have to do is split it up term by term and take the derivative. And we'll get something like, well, the derivative of x squared is 2x. And the derivative of 4, that's a constant, that's just going to be 0, as we learned last week. So if we take, okay, so that's one of our rules. The other rule that we have is that if we have a number that's multiplied by a constant, so let's say 3x squared, and we want to take the derivative of that, all we have to do is pull the constant out front and take the derivative of whatever's left. So that will give us 3 times the derivative of x squared, which will equal 3 times 2x, which equals 6x. Okay. So with those rules, we are now ready to take the derivative over here of this function. So if we want to take the derivative, all we need to do is split it up term by term. And actually, I will go ahead and use this other notation just for fun. You don't necessarily need to write it this way. But we could write that the derivative of 3x squared minus 7. Well, first we want to split it up term by term. So that's going to be the derivative of 3x squared. And Addition and subtraction are not really different in any meaningful way here, so it's going to just be minus the derivative of 7. But that's also going to be 3 times the derivative of x squared minus the derivative of 7, which will end up being 3 times 2x minus 0, which will equal 6x. With this constant multiple rule, what I usually write up here is I usually write this power rule a little bit differently. What I would rather write, just to make it a little bit easier to apply, is if we have something like ax to the n, the derivative is going to be a times n x to the n minus 1. And that's just combining the power rule and the constant multiple rule. So I didn't really do anything new there. I just combined a couple rules together. Let's do one more kind of complicated example before we go on. Let's mix some of these together. Let's do x to the pi. I haven't done this yet, so you'll see what happens. What's the derivative of, we'll go 3x to the pi minus 1 over the cube root of x. Well, what do? First, we're going to go ahead and split it up term by term. The first one is 3x to the pi. And then the second one is 1 over cube root of x. Let's go ahead and take care of this first one because it's easy enough. It's easy enough even though it looks weird. We're going to use the same rule. We take the power out front. And again, we can kind of combine these rules at once. So when we multiply by the original exponent, we're going to end up with 3 pi out front, x, and then we subtract 1 from pi. There's no really fancy way to do that other than just writing pi minus 1. So there you go. So we'll have 3 pi x to the pi minus 1. And in order to take the derivative of the second term, we're going to want to rewrite this as x to some power. So let's do this in a couple steps, I suppose. First, I would write this as 1 over x to the power of 1/3. But really, 1 over x to the power of 1/3, what I really want to do is move that x to the numerator. And to do that, I'm going to go ahead and write it as x to the power of negative 1/3. And now we're ready to go ahead and use that power rule. So again, our first part of the derivative was 3 pi x to the pi minus 1. And here we'll have a negative times a negative, so that's going to end up being plus 1/3. And then our new power is going to be x to the negative 1/3 minus 1, which negative 1/3 minus 1 is going to be negative 4/3. And I won't go ahead and simplify it any more than that. That's fine with me. So there's our answer. So now we know how to take the derivatives of a whole bunch of new functions. So we'll give you a chance to play around with that.